Today we are going to discuss about the concept of simplex method to solve linear programming problem. So the basic aim or the lecture will be based on how this simplex method or the algorithm of simplex method is developed. Okay, what is the theory behind that, what way we will proceed, what is the approach we will follow to get that algorithm, and the next class we will see the exact algorithm. So we will start from the idea which will connect to the previous one. For example, if I do here, if I take the convex region, this, okay, this is the convex region and these are the end point or extreme points of this convex region. Now what will happen? The main purpose is that we have to find the optimal solution. Now how to find the optimal solution, that we are going to see. So for example, this is point P1, this is point P2, point P3, point P4, point P5. For example, this is the point 3. Point 3 is the optimal point. Okay. Now if point 3 is the optimal point, so how to get that point? We have to see. Okay. So one way we can do is that first take a point P1. Okay, initially you take the point P1 and try to search the optimal point. Okay, apart from the graphical method, we have restrictions, like if we have two variables or two decision variable, then we can find out the solution nicely, the representation will be good. Okay, if two or more, means three or more variables are there, then what to do? So that approach we can see, that we can take an initial point here P1 and we will proceed. For example, we will take point P1 and you see P1 is the starting point and P3 is the end point. So we have to go from P1 to P3. So what way we can go? Let first from P1 to P4 we are going. Okay, then we are going P2. Okay, after that we will go to P3. So what will be the path? We can say P1, then P4, then P2, then P3. So this way we can do. So by the search method. But what is the idea behind that search? How to do that search? So that we have to do. That we have to find. The idea, just the basic idea is that by searching we will do. But behind that idea, how to implement that idea and how to reach P3, that is our objective. Okay. So that will give you this simplex method or simplex algorithm will give you how to move from P1 to P3. And in general, P1 we take as the origin. Okay, 0 0. Okay, now before going to see the exact algorithm, we need some preliminaries, we need some concept, then only we can proceed from P1 to P3 and develop the simplex algorithm. So based on that, we have now today, first we will discuss the preliminaries of these concepts. Second, we will have some examples and we will see that through example how these preliminaries can be deployed. Next thing is that we will see how to reduce feasible solution to basic feasible solution. Already we have discussed in the previous classes what is feasible, what is basic feasible. So we will revisit little bit, then we will discuss the reduction, how we will reduce that. And finally at the end we have example problem. Okay, and in that example problem we will see how to reduce a feasible solution to basic feasible solution. So let us start with preliminaries. So preliminaries, first what we have, let us consider an LPP consists of n decision variables and m constraints. You see, number of decision variables are more than number of constraints. So this will come always when you convert the canonical form to standard form, which we have discussed in the previous class. You can refer that if you don't understand. So when we consider canonical form and convert that canonical form to standard form, what we do? We add two things. We add slack variable and we subtract surplus variable to make it equality, to make the constant equality form. Okay, so if you convert that, definitely you will have number of decision variable more than number of constraint or equations. Then the simplex method can reduce an infinite number of solution to a finite number of promising solution. See, if you have convex region, so you will get infinite number of solution, because in that region, if you take for example this, if you take this in between any point, okay, it will have what? Solution. It will give the solution, but promising solution means from the solution, from the set of solution, what set of solution you will get the optimal solution, that will give you the promising solution. Okay, so maybe infinite number of solutions are there, but out of that some finite number of solutions are there which will give you the optimal solution. Okay, so we will see that thing by using the following steps, how it can be done. So carefully you see, after converting the given LPP to standard form, we get m plus n variables. Okay, then the initial solution can be found by selecting n variables, okay, equals to 0, and the remaining m equations are solved to get the solution. Okay, clear? Now the obtained solution exists and is also unique. Here the m variables are called basic variables and they form a basic solution, whereas n 0 variables are known as a non-basic variable. So for example, if I take a11x1 plus a12x2 plus a13x3 equal to b1, a21x1 plus a22x2 plus a23x3 equal to b2. So how many equations are there? Two equations are there. How many variables are there? Three variables are there. So n is 3, m is 2. Okay. Now in this case what we have? N minus m is 1, means you can take one variable as 0. If we take x3 as 0 and whatever be the system we find out, this will be the system. Okay, so this equal to b1, this second a2x1, sorry, a21x1 plus a22x2 will be b2. So this will be the second equation. Clear? Now after putting x3 equal to 0, if you solve that system, you will get x1 and x2. This x1 and x2 are called basic variable and x3 is called non-basic. Okay. So in this case, what we can take? If we take x3, then you will get this combination x1, x2. If you get x2, then you will get x1 and x3 as basic variable. If you take x1 0, then x2 and x3 are basic variable. So three possibilities are there. Depending on the m and n value, you will have the number of combinations, and based on that you have basic variable and basic non-basic variable, and the basic variable which will give the solution, that is called basic solution, and if it is feasible then it is called basic feasible solution. So those are there, we will discuss. So first from the LPP you have to get those things. Step 1, that is next. Step 2, in the step 2 the variables must satisfy the non-negative restrictions, that is variable must be non-negative. So whatever variables we have, let it be we have x1, x2, s1, okay, maybe slack variable 3 are there, then all must be greater than equal to 0. Okay, so this is the non-negativity condition, that is greater than equal to 0. This is the non-negativity condition. But some of the basic solution possess negative valued variable. Like for example, we had x3 as non-basic, and x1, x2 as basic. Okay, in that let x1 is negative value, then what happens, those set of value will not consider, and those solutions are called infeasible solution, which is discarded. Okay, if negative is coming, that is infeasible solution, it will not satisfy restrictions, that's why restriction is greater than equal to 0, either positive or 0, so it will be discarded. As such, the process starts with the basic solution which contains non-negative variables. Then the next basic solution also followed the same non-negative restrictions which ensure the feasibility condition. Such a solution is called a basic feasible solution. If all the variables in the basic solution or basic feasible solution are positive, then it is called non-degenerate solution, and if some of the basic variables are 0, then it is called degenerate solution. Okay, now how to search? So first case you can take x3 non-basic, then proceed what it is coming. If it is infeasible, discard. Okay, if it is feasible, just see and find out the solution and get the answer. Second search you have to do, let x2 non-basic, and then same procedure you have to do. And third, you can take x1 non-basic and the procedure you have to do. And all this if we complete, then we will get the solution, whatever solution is getting, from there we will get the optimal solution. But here one thing is that in that basic solution itself, again, if some of the combination, like if this case I am taking, so in this case let x1 equal to 0. So what will be then solution? 0, x2, 0. So this solution is nothing but your what? Degenerate solution, because at least one variable is 0. Okay, it is written if some of the variables are 0, it is called degenerate solution. If x1 and x2 are positive, okay, value, then it is called degenerate solution. Understand? So this will be meaningful when we will see example problem, we will see those things. So third thing is that what? A new basic feasible solution may be obtained from the previous one by equating one of the basic variable to 0 and replacing it by a new non-basic variable. What I have told just now, first you take x3, first you can take x3, then x2, then x1, like that. This way we will search for the optimality. Okay, the eliminated variable is called outgoing variable. Now if second step from here to here, if you are going, we will eliminate this one. Okay, means we will eliminate this one, we will not consider. So that is called your outgoing variable, while the new variable is known as incoming variable. So this will take, so this will be our incoming and this will be outgoing. Okay, so that way we can search, one will replace another, then we will start the procedure. Okay, so that is the idea. So if we see, if we summarize the idea, what we get, just now you will see, it is noted that the incoming variable must improve the value of the objective function. So whatever be the search we are doing, that must improve the objective function. Improve the objective function means if it is maximization problem, the value becomes more than the previous one, means objective function value. If it is a minimization problem, the value of the objective function becomes less than the previous value. Okay, so that way. So the value of the objective function which should obey the optimality condition, and along with that it will obey the optimality condition. These steps are repeated until no further improvement is possible. So we will search those things till the no improvement is occurred. Okay. Finally, the resulting solution is called the optimal basic feasible solution. Okay. This one. Now, if we again summarize in a single line what we can tell, in other words, we may say that simplex method is based on feasibility and optimality condition. Feasibility is greater than equal to condition, and optimality condition that we know that whether it will be optimal or not, we will check by the previous value and get. Okay. So these are the preliminaries. Now based on this, let us see some example. So first example we have, clearly see those things, it will be very important. So find all the basic solutions of the following system of equations, identifying in each case the basic and non-basic variables. Okay, so we have to identify that. Investigate whether the basic solutions are degenerate basic solution or not. I mean degenerate basic solution or non-degenerate. So those things we will identify. Hence find out the basic feasible solution of the system. Okay. So now you see the question. We have two equations, 2x1 plus x2 plus 4x3 equal to 11. Second equation, x1 plus x2 plus 5x3 equal to 14. So two equations means m value is what? 2, and three variables are there, x1, x2, x3. So n value is 3. That means what is the extra value? Or n minus m will be 1. So one variable first you have to take as 0, then other two variable will be considered as basic solution. Okay. Similarly, we will see all the combination, and then we will find out what will be the basic solution, what will be the non-basic solution, what will be the basic variable, what will be the non-basic variable, degenerate basic solution, non-degenerate basic solution, that we are going to see. So in solution we see those things we have first written, n equal to 3, m equal to 2. Okay. So in this problem, a basic solution can be obtained by setting any one variable equal to 0 and then showing the resulting equation. So hence how many combination we will get? We will get the combination NCM, that means 3C2, that is 3 combinations we will get. So next we will see those in tabular form. So first combination, if you take x1 and x2 as basic variable and x3 as non-basic variable. Non-basic variable means this will be 0. If you take x3 is 0 and x1, x2 as the basic variable, then we will have, this is the reduced form of the system of equation what we had. So the x3 term will be vanished. So we will remain 2x1 plus x2 equal to 11. 3x1 plus x2 equal to 14. Now solve this equation, two equation. If you solve these two equations, x1 value you are getting 3 and x2 value you are getting 5. Now 3 and 5 both are positive value and no one is 0. So what happens if both are positive, then it is called, or it will satisfy feasibility condition, that is xi or xj greater than equal to, xj greater than 0. Okay, if equal to, then it will be a problem, it will be a degenerate solution and all. So as neither of the basic variable is 0, that's why we call it is what? Degenerate solution or non-degenerate solution. It is a non-degenerate solution. Okay, so that's why, is the solution degenerate? The answer is no. Second combination, if I take x1 as the non-basic variables, means x1 is 0, then x1 term will vanish from the system of equations and x2, x3 will be basic variable. Now we will check what will the x2, x3 variable. So the reduced form of the equation will be x2 plus 4x3 equal to 11, first equation. Second one is x2 plus 5x3 equal to 14. So if we solve this two equations, we will get x2 value 3 and x3 value -1. So now -1 is not satisfying the feasibility condition. That's why it is infeasible solution. x2, x3 means 3 -1, x1 is 0, 0, 3 -1 is a infeasible solution. Okay, that's why is the solution feasible? No. Okay, and is the solution degenerate? Yes, it is degenerate. Now third one we will see, basic variable if we are taking x1 and x3, and non-basic variable if we are taking x2, means x2 is 0, then the x2 term will vanish in the set of equations. Okay. So we will get 2x1 plus 4x3 equal to 11, first equation, 3x1 plus 5x3 equal to 14, second equation. And if you solve this two equation, we will get x1 is 1 by 2, x3 is 5 by 2. So all these x1 and x2 value are positive. That's why it satisfies the feasibility condition. Okay, that is yes, it satisfies, and it is not satisfying the degeneracy, means there is no zero value for x1 and x3. That's why it is not degenerate, non-degenerate. Okay, so in this way you can find different combinations. So these are the different set of solutions. First one you can see 3, 5, 0. Second one is infeasible solution, will not consider. Third one is 1 by 2, 0, 5 by 2. So these two solution we can consider, and by putting these two solution, if the objective function is provided, we will get the solution which will be optimal. That we will see. If it is maximization, maximum value we will take, minimization, minimum value of the objective function we will take, and the corresponding solution x1, x2, x3 will be the optimal solution. Next example problem we will see. It is little interesting because we will find out the objective value. So find the optimal solution of the following LPP, compute all basic solutions, and find the solution which maximizes the objective function. Okay, now we have equation, or after converting the constant we will get this equation, that is 2x1 plus 3x2 minus x3 plus 4x4 equal to 8. Second equation is x1 minus 2x2 plus 6x3 minus 7x4 equal to minus 3, and x1, x2, x3, x4 all are positive or equal to 0, and the objective function is that maximum z, 2x1 plus 3x2 plus 4x3 plus 7x4. Okay, so this is the objective function we have. So that we need to find out for which combination of x1, x2, x3, x4 it will be maximum. Okay, now here if you observe, there are two equations. M will be 2. How many variables are there? Decision variable 1, 2, 3, 4. Here 1, 2, 3, 4 decision variables are there. So n equal to 4. That means n minus m equal to what? 2. So difference is 2, means 2 variables we can take 0 at a time, and 2 variables are basic variable, then we can proceed. Okay, so that we can find out all the combination in this way, like 6 different ways we can find out the combinations. So that combinations we will get. So here you can see, first combination we are taking x1, x2 as basic variable and x3, x4 as non-basic variable, means x3 and x4 as 0. If you do that, then the system reduced to 2x1 plus 3x2 equal to 8 and x1 minus 2x2 equal to minus 3. Now what is the next task? Next task is that to solve these equations. If you solve this equation, this two simplified equation, you will get the x1 value as 1, x2 value as 2, and all these two values like x1 and x2 are positive value. If it is positive value, it is satisfying the feasibility condition. Yes, it is satisfying the feasibility condition. If it is satisfying the feasibility condition, next thing is that we can say that it is a basic feasible solution. If it is a basic feasible solution, we can see, and x1 x2 neither one is 0, so it is also non-degenerate. So non-degenerate basic feasible solution we have. So if we get that thing, after that we will find out the optimal value of z. So z, we have the function value given there. We will put x1 value 1, x2 value 2, x3 value 0, x4 value 0, then we are getting this z value as 8. Okay, and whether this is optimal? No, it is not optimal, so we have to proceed further. Okay, proceed further means next combination we can take x1 and x3 as basic variable, x2 and x4 as non-basic variable, means 0. If you take x2 and x4 value at 0, so x2 and x4 terms will be vanish from the set of equations, and the reduced set of equations will be 2x1 minus x3 equal to 8, x1 plus 6x3 equal to minus 3. Now if I solve these two equations, so what will happen? x1 will become minus 14 by 13 and x3 will become minus 67 by 13. So both these values are negative value. If any one of the value is also negative, then this is considered as infeasible solution. So if it is infeasible solution, we will not consider for our investigation. Okay, and we can say that it also not satisfying the feasibility condition because it is negative. It should be positive, then only it should satisfy. Okay, next, then third combination we can take x1 and x4 as basic variable, x2 and x3 as non-basic variable. Similarly, if you apply that x2 and x3 as 0, the reduced equation will be 2x1 plus 4x4 equal to 8, then x1 minus 7x4 equal to minus 3. If you solve, we will get the x1 value as 22 by 9, x4 value as 7 by 9, and both the value are positive. That's why we can say that it will be a feasible solution and basic feasible non-degenerate solution. Okay, and then we will compute the z value. In that z function, we have to apply the x1 value, x2 value, x3, x4, x1 22 by 9, x2 0, x3 0, x4 7 by 9. If you apply, if you put, you will get z value 10 to 10.3. Okay, and it is not optimal till now. So next combination x2 x3 you can take basic variable, x1 x4 you can take a non-basic variable, and if you proceed, then you can see that again we are getting x2 x3 as positive value, that is 45 by 16 and 7 by 16. Okay, and it will satisfy the feasibility condition, and we can say that it is a non-degenerate basic feasible solution, and the solution will be 10.2, which is not optimal again. Then we will proceed x2 x4 basic variable and x1 x3 as non-basic variable. Then we can see that it will give x2 positive value and x3 negative value. Okay, and it is not satisfying feasibility condition, so we will not consider this solution. The final combination we will get that x3 and x4 as basic variable, x1 and x2 as 0. If we take, then this system of equation will convert it into minus x3 plus 4x4 equal to 8, 6x3 minus 7x4 equal to minus 3. And if we solve this two equation, we will get x3 as 44 by 17 and x4 is 45 by 17, and which is both are positive value which satisfy the feasibility condition. If satisfy the feasibility condition, then we can say it is non-degenerate basic feasible solution, and putting this x3 x4 then x1 x2 0 value, we will get the z value, that is 28.9. okay, which is optimal, because if you see 8, 10.3, 10.2, 28.9, maximum value is 28.9. In the problem it was given find out the maximum value of z, means maximize z. So 28.9 is the maximum value, and for corresponding the solution or the variables are x1 equal to 0, x2 equal to 0, x3 equal to 44 by 17 and x4 equal to 45 by 17. So this will give the optimal solution. I hope it is clear. If it is clear, then we will proceed to the next part. Next part is that another solution, means another problem we have, example 3. So using matrix vector notation, so that the following linear equations have degenerate solution. Okay, so 2x1 plus x2 minus x3 equal to 0, 3x1 plus 2x2 plus x3 equal to 3. So again m equal to 2, number of constants or equations, n equal to how many? N equal to 3, x1, x2, x3. Now if we have here the solution x1 equal to 0, then we are getting x2 5 by 3 and x3 minus 1 by 3. So if minus is coming, it is called not feasible, non-feasible. Okay, the remaining solution what we will get, if x2 equal to 0 we are taking, we are getting x1 and x3 0. If I am taking x3 0, we are getting x1 equal to 1, x2 equal to 0. So in this case what is happening, any one of the variable, if I am considering x2 equal to 0, basic variables will be x1 and x3. So in this case x3 is 0, which is one of the basic variable. Similarly in the second case, if I take x3 as 0, means non-basic variable, then x1 and x2 will be basic variable. So out of this x1 and x2 basic variable, x2 value is 0, means one of the basic variable is 0. At least one of the basic variable will be 0, then it is called degenerate. That's why we call degenerate basic feasible solution. Okay, clear? Now we will next we will see the how to reduce the feasible solution to basic feasible solution. This is very important part while applying the simplex algorithm. So please understand properly. So first we will see basic feasible feasible solution. Feasible solution means if your decision variables x1, x2, whatever be the decision variable x1, x2, xn, okay, those should satisfy both the constraint and non-negativity condition, then only it will be called feasible solution. And basic feasible solution, just now we saw what will be the basic feasible solution. If m is less than n, you take a difference of that, and those number of variable you make it 0, other variable will be non-zero. Okay, those things, from that you can take the basic solution, that is called basic feasible solution. Now consider an LPP, m constants and n variables that satisfy m less than n. The constants are in the form of the following equation. You say constants will be in the form of these equations. So a11 x1 plus a12 x2 plus and so on plus a1n xn equal to b1. This is the first constant, equality constant. Second equality constants will be a21 x1 plus a22 x2 plus and so on plus a2n xn equal to b2. This is the second equality constant. Similarly m equality constants will be am1 x1 plus am2 x2 plus and so on plus amn xn equal to bm. Now this, if I write into matrix form, how it looks like, the coefficients, if I see the left side of the equation, and the coefficients are nothing but a11, a12, a1n, a21, a22, a2n, am1, am2, amn, those are the coefficients. So that we can write in matrix form, this A, where the first row is a11, a12 and so on, a1n. Similarly, if we write the last and the mth row will be am1, am2 and so on, amn. Okay, suppose there exists a feasible solution, then this feasible solution can be reduced to basic feasible solution if we consider the following step. What are the steps we are going to see? We will see. So this set of equation we can convert into this ax equal to b equation. okay, in matrix form. But what are the steps that we will see now? So carefully you can see. First, okay, if the column of the vectors are linearly dependent, then we have we may express the following. We may express the column vector Vj, that is a1j, a2j and amj transpose belongs to A, that is j equal to 1 to n, as linear combination on the other columns vectors. That is for scalar alpha j, we may write Vj equal to alpha v1 plus alpha 2 v2 plus and so on plus alpha and vn. Now for example, for understanding what I will tell, let us see two equations, that is a11 x1 plus a12 x2 plus a13 x3 equal to b1. Okay, a21 x1 plus a22 x2 plus a23 x3 equal to b2. Now if I write this in matrix form, how it looks like: a11, a12, a13, a21, a22, a23. Clear? Now here if you see this in this matrix, what happened, the vector, if this is our vector v1, means a11, a21. If this is our vector v2, a12, a22. If this is our vector v3, that is a13, a23. So what happens, you see, this is a 2 cross 3 matrix. So what will be the rank? Maximum the ranks will be 2, means whatever be the minimum value of this row or column, so that should be the rank of that matrix. So rank of the matrix will be 2. If the rank of the matrix of this matrix, if I am writing A is 2, if a rank of A is 2, that means there are 2 linearly independent vectors, means either v1 v2 or v2 v3 or v3 v1. So other is the extra one, which is depending on the other 2 vectors. So what we can write, we may write that v1 equal to the combination alpha 1 v2 plus alpha 3 v3. Yes or no? We can write. Okay. Similarly, we may write alpha 2 equal to some maybe beta scalar beta 1 v1 plus beta 2 v3, like that. So means any one of the column vector, any one of the vector we can write in the form of means linear combination of other 2 vectors. Okay, so that we are going to see in the first step. So that's why Vj equal to alpha 1 v1 plus alpha 2 v2 and so on alpha and vn we can write. Means if I take v equal to v3, here v3 you can write alpha 1 v1 plus alpha 2 v2. Understand? Because and this is obvious, because always we will get n equal to greater than m value. So this type of matrix you will get. You will not get square matrix. Okay, out of that you can get this combinations, means any of the vector will be combination of other vectors. Okay, so if that is the case, what is the second step we are going to do? If in that case, second step we have to do is compute the ratio xj by alpha j. So what is xj? So we will start with feasible solution. So if the feasible solution is having our decision variable maybe x1, x2, x3 and we have those values, then xj is the jth value. Okay, jth decision variable and its value. So xj by alpha j we have to find, and we have to see that alpha j must be greater than 0. So xj by alpha j we have to find, compute and choose the minimum of the value. Means we have to find x1 by alpha 1, x2 by alpha 2, x3 by alpha 3, all the combination we will take provided the alpha j greater than 0, and out of those we have to select which is the minimum ratio. Okay, so we have to find minimum of x1 by alpha 1, x2 by alpha 2 and so on. Okay, maybe xn by alpha n. So those things we are going to see, or here we are writing xk by alpha k. So minimum one we have to find. Next thing, that step 3 is reduce the value of the variable corresponding to the minimum value or minimum ratio xk by alpha k to 0. Okay. Then fourth one, the values of the new variable looks like this: xj dash equal to xj minus xk by alpha k into alpha j. Okay. Now these 4 steps we are going to see in the through example problem. So we will see this example problem. So here we have feasible solution. This means from here we are going to start. So x1 is given 2, x2 is given 4, x3 is given 1. Now using this feasible solution we will proceed and we will find out the next one. So the equations what we have given: 2x1 plus x2 plus 2x3 equal to 2, x1 plus 4x2 equal to 18. These two equations we have. So from these two equations we will reduce the given feasible solution. This is the feasible solution that we have to reduce to basic feasible solution. How to do? Let us see. So in matrix form, if you write this equation, it will be coefficient matrix will be 2 1 2 row wise, second row will be 1 4 0, like, and right side vector is 2 18. Okay, you can see this coefficient matrix, it is not a square matrix. Okay, there are 2 rows and 3 columns, means any one of the vector, like this one is vector, this is second vector, this is third vector. So any one of the vector can be written in terms of other vector. Okay, for example, if I want to write 2 1, so 2 1 will be maybe alpha 1 into 1 4 plus alpha 2 into 2 0. Okay, so if you solve it, you will get some particular alpha value. Okay, this linear combination is giving 2 1. Okay, now we will see those things. So first step is that we see, as the rank of A is 2, we may write to any one of the vector vi, that is I 1 2 3, as linear combination of other two. So v3 I am writing v3 equal to alpha 1 v1 plus alpha 2 v2. That v3 was 2 0, so 2 0 I can write as alpha 1 2 1 plus alpha 2 1 4. Okay, now this is the thing here. From here what you are getting, 2 equal to 2 alpha plus 2 alpha 1 plus alpha 2, then second you are getting 0 equal to alpha 1 plus 4 alpha 2. So in this two equation, by substituting this alpha 1 value in alpha means first equation, alpha 1 of second equation, if you are putting in first equation, you will get alpha 2. By substituting or by solving any other method, you can get alpha 1 and alpha 2. So what will be the alpha 1? Alpha 1 we are getting 8 by 9. Alpha 2 we are getting minus 2 by 9. Okay. Now if you want to check, then you can check again by putting alpha 1 alpha 2 in this equation. If you put, it is satisfying. Okay, if satisfying, we can take that alpha 1 8 by 9, alpha 2 is minus 2 by 9, then alpha 3 will be minus 1. Okay, so alpha 3 you can get by other combinations, or here from this equation you can find out. This is alpha 3. Okay, because minus 1 is multiplied with 2 0. So alpha 1 alpha 2 alpha 3 is known. Now x value we know, so we have to find out the ratio. Okay, xj by alpha j. So x1 is 2, so 2 x1 by alpha 1. So x1 is 2, so 2 by 8 by 9 we have to find. So if you solve it, it will be 9 by 4. Okay, similarly second one, x2 equal to 4. So x2 by alpha 2 is negative, so that 4 by minus 2 by 9, and alpha 3 is minus 1, x3 is 1, so 1 by minus 1. So as alpha is negative in these two cases, so we will not consider those things, and only thing left is this: if other values are there and non-negative, then it's fine, we will consider those things, but we will take the minimum out of that. So minimum is 9 by 4 we are getting here. So if 9 by 4 we are getting that factor, so that factor will be multiplied. Okay, so x1 dash will be what? X1 minus that factor into 8 by 9 alpha 1, okay, equal to 0. Then x2 will be, x2 dash will be x2 minus that factor into alpha 2, that is we are solving 9 by 2 we are getting. Then x3 will be x3 dash will be x3 minus that factor 9 by 4 into alpha 3. If you are doing, then you are getting the value 13 by 4. So these three values will give the solution. Means first one is getting 0, second one is 9 by 2, third one is 13 by 4. So this is therefore the required basic feasible solution is this. This is the basic feasible solution. Here we can take this x1 value as 0, then x2 and x2 and x3 value are positive value. So we can say that it is non-degenerate basic feasible solution also. Okay, clear how to find, how to convert a feasible solution to basic feasible solution. So this technique, this idea will be used in the simplex algorithm that we are going to discuss in the next class. So the exact algorithm what we will see in that class, we will use all these concepts. So be ready with this concept, be thorough with this concept, then only you will understand the next concept. So these are the references which you can use for this content what we have discussed.